So here's our structure where we see all four transformations in their spots. The A transformation multiplied to the function out front, D added, or if it's negative, subtracted from the function. B and C are working directly on the variable in the function. B is multiplying, C is added or subtracted if C was negative. And let's talk about an example that you would have to handle. Given this function, we want to come up with the amplitude, the period, and the phase shift. So remember that our A transformation is the amplitude, the number right out front. I can see it readily. I see it negative 1.5, but amplitude, since it's a distance, we always use a positive number. You could say absolute value of A should be our amplitude. So we'll go with a positive 1.5 for the amplitude. It's just bad form to use a negative number for amplitude. We want to recognize that quantity is always considered to be positive. Next, the period. We know that we look at the B transformation for the period, but we need to do 2 pi divided by that number. 2 pi divided by 3 is our new period. Remember, by default we start at 2 pi if we're dealing with a sine function, and dividing by B gets us to our new period, 2 pi over 3. The phase shift, we're looking at this pi over 2, and we have to divide that by B as well. Pi over 2 divided by 3 would be pi over 6, and it's a negative in here, which we know is shifting to the right, so we want to come up with a positive phase shift, positive pi over 6. And thinking about, use that expression negative C over B, that would also lead to this result of a positive pi over 6. Now let's look at the graphs. We're going to talk about how you might come up with, if you had to make some graphs by hand, how would you graph this function right here? Now we have access to tons of calculators and computers that make graphs for us, so I'm not going into tremendous detail here. But basically, you start with the base function. So I make my graph of sine. We know how to do that based on some main increments on the unit circle and those ordered pairs. Now one by one, I'll introduce these transformations. The first one I'm going to do is the B transformation. I'm going to change the period. I know that this was a sine of 3x. Now I'm ignoring the negative 1.5 out front. I'm ignoring the plus 1 and the minus pi over 2. I'm just doing transformations one at a time. So the one I'm doing right now is coming up with sine of 3x. Doing this by hand, every point that I see on maroon, I'm dividing my x value by 3. So a peak at 90 degrees divided by 3 is now at 30 degrees. The intercept at 180 divided by 3 is now at 60 degrees, and so on. I pick a few points, I scale each one of them back by a third to produce gradually the graph in green. So I've got sine of 3x that way. Next transformation will be the A transformation. I'll multiply by negative 1.5. Since we're multiplying by a negative, I have to do two things. Not only stretch by 1.5, but also reflect on the x-axis. So basically, any point that I have above, it's going to get swapped down below, and at the same time I'm going to increase by a factor of 1.5. So our valley down here at negative 1 is now a peak, and stretched out to 1.5. The peaks at positive 1 have now been flipped down and stretched down to negative 1.5. That's how I'm coming up with the graph of negative 1.5 times sine of 3x. Next, I'll work in the phase shift. True, we had 3x minus pi over 2 in parentheses, but I know that I do C over B to get that actual phase shift, pi over 6. And we had a positive, so we're shifting to the right. Pi over 6 is 30 degrees, so there's our 30 degrees. Got that going on all over. Wherever we see a point in purple, we shift it to the right by 30 degrees. There's our graph of negative 1.5 times sine of 3x minus pi over 2. We only have one transformation left, the plus 1 at the end, and that's our vertical shift. So every point is now being shifted up one full unit. Where my peaks are at 1.5, now they're at 2.5. The valleys, which were at negative 1.5, have been shifted up 1 to negative 0.5. And my intercepts here at 0 now are seen here on this line at positive 1. So every point picked up and moved up 1 unit, and there's our final graph including all of those transformations. Let's do another example. First, the amplitude. Okay, that's the gimme, it's this number out front, so our amplitude 2.4. Next, the period. We know 2 pi, because it's cosine, start off with 2 pi. 2 pi divided by 1/2. We remember this 1/2 is actually doing a horizontal stretch, and the 2 pi divided by 1/2 is 2 pi times 2. 4 pi is our new period. And lastly, the phase shift, c divided by b, and flip signs, pi over 6 divided by 1/2. So again, that's times 2. That's going to lead us to a positive pi over 3. And let's go through the steps of coming up with this transformed graph as well. Now we're starting with cosine function. Let's do the change in period first. So look at cosine of 1/2 x, and we get there by a horizontal stretch. Everything is now moved twice as far away from the y-axis as it was. This point right here at the intercept, instead of being at 90, now it's at 180. This valley down here at 180, now it's at 360, and so on. Everything has been stretched by a factor of 2. The next transformation I'll do is going to be the vertical stretch, the times 2.4. So every peak used to be at 1, now they're going to be up at 2.4. All the valleys from -1 are going to be pulled down to -2.4. Next transformation will be, well, we only have one left in this example. We had inside the cosine 1/2 x minus pi over 6. We did the math and showed that it's a phase shift of a positive pi over 3. That's 60 degrees. So I'm going to take this last graph and shift every point to the right by 60 degrees, and there's our final transformed graph. Last example, just to touch on tangent one more time. Amplitude is not really used in the context of tangent functions. That's really more so for those wave functions, sine or cosine. So we'll skip amplitude. Phase shift as well, not really used so much with tangent functions, but at period is really the one that I'd like to make a point out of anyways. So we're only going to talk about period for the tangent function. We know that we look for this coefficient on x, but we start with our initial period and divide by this number. And I wanted to point this out because what is period of a tangent function, tangent of x? It's not 2 pi, it's just 1 pi. So in this example, we'll take our starting period, which is just 1 pi for a tangent function. We still divide by the coefficient of x. It gives us a new period of pi over 2. And let's look at this graph. Start with the base function tangent of x. Now we'll change the period. Graph the function tangent of 2x. So every point that I see is now being brought half as far from the y-axis. Instead of this point out here being at 180 degrees, now it's divided by 2 back here at 90 degrees, and so on. So here's our graph of tangent 2x. Our period has now been shortened from 180 degrees down to 90 degrees, or pi over 2 radians. Next, we did have a horizontal shift adding pi over 2. And it's working the same way, where we have to really think about that constant c divided by b. So a shift in this case, it's not pi over 2. Pi over 2 divided by 2, or pi over 4, which is 45 degrees. So our shift, horizontal shift, we can now see it's 15, 30, 45 degrees. We can't tell if it's to the left or to the right, but our phase shift, what we know about horizontal shift, tells us that this is actually a shift to the left. We're adding in pi over 2, that is a shift to the left. So there is our final function incorporating those two transformations, and we're cautious about using the period that we know. We start off with a period of 2 pi for cosine and sine, but a period of just 1 pi for tangent. Let's do a quick recap of these transformations. A was the amplitude, and left over from our original thoughts of function transformations, what we know about A is that it will do a vertical stretch when A is bigger than 1. It will do a vertical compress when A is between 0 and 1. And if we have a negative A, it's also going to reflect on the x-axis. This B parameter is some sort of horizontal stretch or compress. It's a horizontal stretch for numbers between 0 and 1. It's a horizontal compress once we deal with numbers greater than 1. And if we end up with a negative value of B, it's also going to do a reflection on the y-axis. In terms of our period, we would find period by doing 2 pi divided by B, but we would only do that for sine and cosine, which start out with a period of 2 pi. For tangent, it would be 1 pi divided by B. Now the C transformation, we said that to really see what the horizontal shift, what that phase shift would be, we had to do C divided by B. And I'm going to show you now, algebraically, why that is. The C transformation, the constant added to the variable, is really not shown right here. We're actually adding C not to x, but to this product B times x. If we want to really illustrate what is being added only to the variable, the way to do that is to factor this B off of the x. So we're going to bring a B outside with x in parentheses, x plus some quantity. And remember, when we factor out a common factor, it's because we're dividing it out. I've divided B out from the bx, leaving behind just the x. If I divide B out from C, I don't know what those numbers are. I can't tell you what it's going to divide to equal. All I can do is call it C over B. That's me dividing the B out and putting it out front, but it's going to leave behind a C over B. And if I think quickly about doing a distribute, it will definitely take me back to bx plus C. So now we're actually seeing this quantity that is added to the variable, and this is why we need to do C divided by B to really understand what our horizontal shift is. And also, I have a plus C included here, but we'll want to know that a plus C means shift to the left, a minus C means shift to the right. So left if we're dealing with a positive C over B, right if we're dealing with a negative C over B. But if we're talking about phase shift, I would say find your phase shift by doing a negative C over B, because we would like phase shift to be positive when we represent shifting to the right, and phase shift is negative when we represent a shift to the left. Last one is D. D is a pretty simple one. It's the vertical shift, shifting it up when D is positive, shifting it down when D is negative. So knowing these transformations take on a little bit of additional significance with these trig graphs, especially talking about amplitude, period, and phase shift.